Thank you for this invitation to give a talk to this meeting. It's really an honor and a real pleasure to be able to talk about how to interpret the magnetic polarization in CP stars. These are stars I have worked on for 50 years. And yeah, I want to share some of my findings, impressions, and what has to be done. You see, I will speak on physics, on algorithms, tests, and errors. For a long time, algorithms, you know that they govern our life. Amazon just lives with the help of algorithms, but CP stars, they should be governed by physics and not algorithms, something that has gone wrong over the past decades, and I want to point out a few problems arising from this. Just a few words on CP stars. They are peculiar stars in upper main sequence with very conspicuous over or underabundances of a number of chemical elements. They can be very overabundant, for example, rare earths, 3 decks or even more. And some of these CP stars exhibit spectrum variations. The iron peak elements can vary, and so can the rare earths. And quite often, this is in antiphase. So this has to be explained why they are in antiphase. And many CP stars, that's the most important thing, are characterized by strong magnetic fields that are organized on a large scale and which give rise to very important circular and linear polarization. So starting at the very beginning of the study of magnetic fields in AP stars, that was back in the late 1940s by Babcock, and he recorded 2 spectra in the left circularly polarized light and right circularly polarized light simultaneously on a photographic plate, which just involves Stokes I and V. And of course, this is not sufficient to derive the vector field, but it gives you the longitudinal field, which they called the effective field. And to determine it, you have to measure the difference in wavelength between the centers of gravity of the spectral lines. The effect is very small for these stars. And of course, with photographic plates, it has been quite a problem with all the noise in the spectra. But it's amazing what these people at that time could detect. For example, here, a classical magnetic star, HD 125248, and it turned out that the magnetic fields of these CP stars are all periodically variable with the same period as the light variations. And here for this star, there's the plot of line of sight field component. And as it turns out, it is largely sinusoidal, this variation with, well, it can be a bit deformed, but in general, it's more or less sinusoidal. And the way how people tried to explain this right from the beginning, the first idea was some oscillations of the magnetic field, but this went on only for a few years. Then the oblique rotator was proposed and shown to be the most successful model. So here you see the assumption. You have a star with the rotational axis here to seen K, and you have a dipole, a simple dipole centered at the center of the star and inclined with respect to the rotational axis. And when it rotates, the magnetic field you can observe, it's varying, and it's varying more or less sinusoidally. And So at least it was a first idea how to model these stars. In later studies, the dipole was displaced from the center along the axis by a few tenths of the radius. And so this introduced one more free parameter. The free parameter is always something useful as long as it is physically motivated. And still later, it was found that for a few stars, the mean field modulus, which was called HS, could be determined in some stars which are very slowly rotating and which have very strong fields of the order of many kilogauss. And when these fields are organized on a large scale, you can see that, for example, there on the right side, there are Zeeman doublets that are resolved. Zeeman doublets are those Zeeman patterns where the pi and the sigma components coincide. And there it's very easy to determine directly this mean field modulus integrated over this whole visible surface. And of course, later on, like here in the middle, it was much, you have got a much better resolution. Interestingly, there are a few lines, so-called magnetic null lines, which do not split in a magnetic field. For example, the iron line at 4065 angstroms. And you see the difference. This is in Beta Coronae Borealis. You see the intrinsic width of the spectral lines in this star, which reveals a very slow rotational velocity, and the magnetically split lines, which are most lines with complex patterns are not resolved. Taking these together, you have now the variations in HS and in HF. And when you look at them for some of the well-observed magnetic stars like Beta Coronae Borealis and others, there you see there is a phase shift between HS and HF, which means the models for the magnetic field cannot be axisymmetric. Back in 1975, I proposed a non-axisymmetric tilted eccentric oblique rotator model. It was very successful. It looks like that. 11 years later, after I had proposed it, it was really detected and modeled in Uranus. So it means you have a dipole offset from the center of the star, and the dipole axis needs not go through the center of the star. So this already makes it non-axisymmetric, but it also does not need to lie in the meridional plane. So it can completely tilt it offset, and this gives you the possibility to explain these phase shifts. For example, for the strong line field star HD 145708, the model that fits the variation in the effective field and the surface field and the profiles of two silicon lines looks like this. On the top, there's a field strength, and in bottom, the field direction, and you see you get the warped magnetic equator. It's no longer this straight equator, but it's warped. And yeah, if you try to fit anything with axisymmetric models with this star, of course it fails. So you have to have non-axisymmetric models. It might be such a dipole or something more complicated. These models are not unique, so intensity spectra might not suffice, as I showed already in 1991 together with Marcel Goossens. And if you look at different models that give the same good fit to HS and HF, the intensity spectra, especially the wings, often can help to identify the right model. But for example, in the case of Beta Coronae Borealis, completely different models give more or less the same good fit to the wings. So you need more information to get a unique model. Just to show what happens and what you have to explain, spectrum variation in the CP stars with the spots. There, down here, you see the chromium lines. They, for example, at one phase, they are strong. At another phase, they are quite weak. But at the same time, when chromium is weak, europium or calcium gets stronger and vice versa. So we have these antiphase variations, which means that spots or whatever explains these variations are to be found at different places. There had been, back in 1969, the attempt to map the spots, the equivalent widths in the famous star Alpha Tucanum Menaticorum. And when you look just at the equivalent widths and the radial velocities of the spectral line, then you see that the rare earths, they concentrate near the magnetic poles, and the iron peak elements are more prominent near the magnetic equator. In this analysis, the magnetic intensification has not been taken into account. This magnetic intensification is the increase in equivalent width that is due to the magnetic field, and that makes this analysis is a very, very first approximation, but you have to do more than that to model these spots. And that's what started Doppler mapping. Doppler mapping, you assume a star and you take equal area pixels, and in each pixel you assume a certain abundance, for example, of an element. And when you do it in just one pixel, then you see that there's a tiny feature and it travels through the line with the rotation. And what you have to do is just to fit the line or a bunch of lines, the exact profiles, by changing the abundances at each surface element. That might be typically 1000, and to have it converge, to have a perfect fit to the profiles, which is in itself a very straightforward, very easily implemented algorithm. A student of mine wrote a simple Zeeman Doppler mapping code in less than 1 month. But of course, then all to make it really very convincing, you have to invest a lot of time, and and there you need some good algorithms. For example, Doppler mapping is an ill-posed problem, and it's completely underdetermined, even if you neglect anything like stratifications or so. And you need a regularization function so that you, among the thousands and millions of solutions, you constrain it to a most likely solution. So for example, you can have maximum entropy. So you try that your map has the minimum information content, or Tikhonov regularization, you look for the smallest local gradients. And well, Tikhonov regularization is nothing else than a kind of generalized discrepancy principle. It's purely mathematical. It has nothing to do with physics. And for CP stars, Tikhonov has now prevailed over the last 2 decades. Maximum entropy is used for late type stars and for all kinds of non-CP stars, but for CP stars we are just faced with Tikhonov. You have, of course, to test your your code. And the question is, how do you test it? For example, one of the very first attempts, Vogt in 1987, I think it was, he adopted, he just put his name on the star, and with very high contrast structures, very dark characters on a very bright stellar surface. And of course, in this case, there is no physics involved. So mathematical convenience, in that case, a maximum entropy is quite okay. And you get some very reasonable results. Another Doppler mapping test done starting from 2002 with Tikhonov. Here these plots are taken from Kochukov in 2014. You assume 3 well-distributed abundance spots with very high contrast, and then you invert, and then you get something. In that case also, you assume a magnetic field, but it doesn't enter the physics of the star spot. So you can use Tikhonov, that's absolutely legitimate. But when you plot the difference, as yet unpublished, I did it, just extracted it from these plots, and you get local errors of about ±1 dex, which is quite a lot when you look at the contrast of 1 dex. Incidentally, Kochukov in 2002 said that the mean error of this recovery was 0.04 dex. Well, I cannot reproduce that. Because of this inhomogeneous distribution of chemical elements, there had been discussions at the beginning how to explain it, and starting from the 1970s with Michaud, radiative diffusion has remained the only explanation how to explain it. So Michaud proposed that selective radiative levitation, acceleration of certain elements, will lead to overabundances and gravitational settling for other elements that are not driven out by radiation. They create underabundances. And of course, all of this depends on the radiation field, where the maximum of the radiation is in the spectrum, on the distribution of the spectral lines, whether they are more to the ultraviolet and hot stars or whether they are more to the red. So it's, for every element, it's different. And later on, Vauclair and collaborators in 1979 looked at the role of magnetic fields, which of course modify diffusion. We know from the sun how magnetic fields modify the velocities across the field lines, and Vauclair applied this to the magnetic stars and radiatively driven diffusion, and showed that there's a great reduction in the diffusion velocities of charged ions. So here just a few results which I obtained together with Georges Alessian over the last 25 years. And you see diffusion leads to stratified abundances. And these abundances, they depend on the magnetic field direction in the first, well, mostly on the field direction and also on the field strength. So for example, here it's a 12,000 Kelvin atmosphere, and there's a magnetic field of 7.5 kilogauss. And there you have the different inclinations of the magnetic field with respect to the stellar surface. So in black, it's the horizontal, to the normal. So zero is vertical fields that have very little influence on the diffusion, and The green one is a horizontal field, and you see it greatly modifies the diffusion, and you see the increase in abundances can be quite important. It can be one dex, the other fields and other elements. Here it's iron, which show much more effect of this effect. And these stratifications are in general non-monotonic. They depend, as you see, non-linearly on the direction of the field. And if you look, for example, for chromium, what happens at a certain field direction, 75 degrees, and a field of 1 kilogauss up to 20 kilogauss, and you see very high up in the atmosphere, you still, even despite the fact that the field is very weak, you have a large increase in abundance. And the stronger the field is, the stronger these abundances already grow in deeper layers. And usually these stratifications have been approximated by step functions, simple step functions, but as you can see, that's not a good approximation. There's another effect that plays a role, that's mass loss. We don't know exactly how to model the mass loss and how to estimate the mass loss in CP stars. It's very low, but even a very low rate of mass loss can modify the stratifications to a very large degree. Of course, again, the largest for, the mass loss is also expected to change with the field direction. When the field is normal to the surface, then you're expected to have a larger mass loss than when it's horizontal. But that's very difficult to model, and so one can just show what happens and what we have to be prepared to take into account. And there's the real problem that has continued for a long time. I call it Tichonovization of CP stars. So everything where you could apply Tikhonov regularization has been done, well, without regard to the underlying physics. For example, if you assume a global stratification, then Tikhonov helps you to get some curve, but this curve is unphysical. And of course, in magnetic fields, as in this star, which had been analyzed by Kochugov and others in 2006, there can be no global stratifications. And much later in 2009 and again in 2016, there had been this attempt to minimize local step functions, to minimize the difference here between the lowest and the highest value in the upper layers, the same in the lower layers, the same between upper and lower layers, and the position and the width of the step. And well, you get the result, but it's incompatible with everything we know about field-dependent diffusion. So it's Tichonovization, nothing else. And if you apply it to a star like 53 Cam, there it had been used, it had also been used to a magnetic field, just without introducing any global constraints on the field structure, not even divergence B equals 0, then you get these results. And now it's called up to 2015, it has been called discrete surface element inversion, but it's unphysical because you don't have magnetic monopoles. At least so far, nobody has detected them. And then look at this, at phase 0.60, you have magnetic fields there where the field is mostly or entirely horizontal. You have very low field strength, and just at a very short distance, you have a very strong field. And the difference in field pressure, magnetic field pressure, is about a factor of 10. So how can this remain stable? Well, I can tell you it cannot. And if you look at such a Tikhonov field and compare it with what Maxwell said, and the authors of the 2004 papers, they have not really looked at a paper already published in 91, and they have not thought of Alfvén and what he had said about magnetohydrodynamics, and what they got, and they admitted it themselves. There's a very large flux imbalance, and this map does not satisfy equation 15, which means divergence B for this map is largely not non-zero. And one thing that's obvious, that this discrete surface element inversion can never ensure this divergence B, because parts of the star remain invisible. So for another violation of the laws of physics, we can look later. And there I started musing on Tikhonovization. There is a famous quote by Mencken: explanations exist. They have existed for all time. There's always a well-known solution to every human problem, neat, plausible, and wrong. And then, of course, Jorge Luis Borges, in his Ucpa Orbis Tertius, we have, I get the impression when I look at these maps of 53 Cam and of other stars, ahora tenía en los manos un vasto fragmento metódico de la historia total de un planeta desconocido. And you can read the rest. My Castellano is too bad. It's better you read it. So it's something that has nothing to do with physics. And when you overlook and you don't take into account fields of 7 kilogauss or 2.5 kilogauss, as in these cases, suddenly you find that silicon is as abundant as hydrogen, and iron and manganese as abundant as helium, or everything based on non-magnetic line synthesis, or for another star which has been treated in a non-magnetic line synthesis, you find unprecedented details, a high level of complexity, but it has nothing to do with the real surface abundances, because the magnetic field, influence of the magnetic field, magnetic splitting has not been taken into account. And also, how could iron hurricanes be avoided? If you really believe that iron is so abundant in one place and almost underabundant in other places, or the same for silicon. If you look at the run of gas pressure with geometrical height, then you see if you have solar iron and iron 3 decks overabundant, then you have a huge difference at the same distance, vertical distance, the same vertical position. You have several orders of magnitude difference in pressure. So how can this be stabilized? If you don't have a stabilizing force, pressure equilibrium would be attained almost instantaneously. But there is no such force. That's one point. And the other, has any one of you ever heard of a stellar atmosphere with 50% silicon and 50% hydrogen? I have never seen anything. And with the usual codes, you cannot calculate it. There you see what can happen when you don't take into account the magnetic field, when you invert your observations. There you have the same magnetic geometry in all 4 plots, and you get spurious abundances and fantastic values of the fit to the lines. And for the same, depending on the line, on the field strength, rotation, and Zeeman pattern, you get different spurious abundances. So you have to take the magnetic field into account. That's absolutely necessary. So we had the problem with divergence-free models and with models that were not divergence-free. And how can you ensure that that divergence is always 0? That's Jardine et al., who introduced the potential field and everything expressed in terms of spherical harmonics. And to fit the profiles, you have to iterate on the coefficients until everything fits. And what you need, as you see here at the surface, with R equals 1, you have 1 coefficient per mode. So that's feasible, that has been done. But yeah, for example, the potential field of the Earth, it's well known. Here is the International Geomagnetic Reference Field, the 13th generation, and they go to a spherical harmonic degree of 13. In CP stars, it had been mostly 10, but for a few, it has gone up to n equals 20. Here, the field values are in nanotesla instead of the usual Gauss and kilogauss for CP stars. Donati and co-workers, and later Kochokov, they added toroidal to the poloidal components. And of course, in that case, you have no longer potential field. And there's another modification. The radial field is no longer coupled to the horizontal field. So you have alpha, beta, and gamma. So you have now 3 parameters per mode. Donati applied it to a 500 Gauss field, which is not too bad. That's probably legitimate, but Kochokov used it for CP stars with very large fields. And it has been known for a long time, but Braithwaite and Boyd published it again in 2017. Fields in CP stars are force-free. When the plasma beta, this ratio between the gas pressure and the magnetic pressure is very large, much larger than 1, then it's the gas pressure that dominates completely, and the field geometries can be anything. But when beta is very much smaller than 1, the field has to be close to force-free. And Braithwaite and Boyd say even for the weakest CP stars, beta equals 1 coincides with the photosphere. So for strong field stars with several kilogauss or up to 20 kilogauss, of course, these fields must be force-free, absolutely. And for 43 CAM, for example, Babel and Michaud had already found in 91 that the magnetic pressure is larger than the gas pressure, down to very deep layers. So 53 CAM should not only be divergence-free, but force-free. And all of this is not given. If you look at current-free fields in spherical coordinates, this is the expression for curl B. In this, the finite conductivity of the CP star atmospheres means that these atmospheres must be force-free. Curl B cross B equals 0. And since there cannot be on the long term any strong currents, they have to be potential. And so, which means curl B equals 0. And that's this formula. And to be current-free, potential donor these fields, the poloidal part, their beta must be minus alpha for every single mode. And if you look at the fields mapped and published so far, none of these are current-free or even just forced-free. So it means they are unphysical. Just a few words on toroidal fields. If you look at the classical paper of Winch et al. In 2005, toroidal fields imply electric currents, and there it's the same. These electric currents, how can these fields created by these currents remain stable for years or even decades? And Mestel and Moss, they presumed that the observable toroidal fields will decay and disappear over very short time scales. And for example, when you find published results in 49 CAM, that 20% of the energy is in the toroidal component, that again looks quite unphysical. But you can do more if from the published maps, if there is a potential field, then it is possible to reconstruct the horizontal field from the radial field. Geophysicists do it all the time, and they helped me to do this. And for a star like HD 32633 with fields of more than 15 kilogauss, that's the horizontal field that has been published. And if you calculate the horizontal field from the radial field, assuming that the radial field is potential, then you get this. So it clearly contradicts. And if it's not a potential field, then it violates the force-free condition. And these stars here, the field must be absolutely force-free. There's no way around it. Another one is HD 119419. Again, the horizontal field is published, and that's what you get from when you calculate it from the radial field. And there, 32% of energy is in the toroidal component, according to Rusomarov and co-workers. And again, that's not unphysical. Well, again, citing Este brave new world is obra de una sociedad secreta de astrónomos. Los metafísicos de pleno buscan la verdad, ni siquiera la verosimilitud, buscan el asombro. Y la literatura de UPA era de carácter fantástico, y que sus epopeyas y sus leyendas no se referían jamás a la realidad. Looks quite as what has been published for these stars. And now, at last, there is also the question of uniqueness. If you see that you can model these stars by assuming a magnetic field that's unphysical, that violates the basic laws of physics, and you still get a good fit to the observed profiles, then there's something with some problem with uniqueness. It has always been said you can get the unique solution with the help of Tikhonov. And so, as I showed at the beginning, when you have just HF and HS, and if later you add Stokes I, and then you extend it to Stokes IQUV, can we then be sure to obtain unique models? And back in 2005, Piskunov said, yes, we can. We show that the underlying inverse problem based on all four Stokes parameters is well posed and thus has a unique solution. Only when one reads it more or less carefully, it refers only to the magnetic field and only to the magnetic field in the absence of chemical inhomogeneities. So there can be no spots, there can be no stratifications, especially stratifications that depend on the magnetic field. In that case, there is no reason to believe that this problem has a unique solution. And if you look at the maps published by the members of this Uppsala group, they contradict this picture, and I'll show you that. For example, you have HD 119419, where it can be shown that the field is non-potential, it violates the force-free condition, and still you get wonderful fits to Stokes Q and the other Stokes parameter. So this means you get really something that looks like a good model, a unique model, but it cannot exist in nature. So you can only conclude that there exist various geometrically, but not physically feasible magnetic and abundance models. You can go further. 49 CAM has been analyzed several times in all 4 Stokes parameters. And I showed just published maps for 2 phases for 2007, 2011, and 2017. And the fits to the profile were always said to be very satisfactory by the authors. But if you look, for example, from 2017, if you look at Stokes Q for a chromium line, the observations are this histogram, this black curve, and the best fit with multipolar, with the spherical harmonics, is the blue line. But you see there the blue line goes just in the opposite direction from what the observations are. So there is not a really good fit, and obviously for this about the same quality of fit, sometimes you get, as here, a not very extended spot. Sometimes it's an equatorial belt. Sometimes it's something still different. So you cannot say that you have ever obtained a unique model of this star. Then Alpha 2 Canum Venaticorum, it's the same. And there the field modulus again at 4 different times. And there again, just look at these lower ones. It's, yeah, again, the magnetic field strengths and the geometries are unphysical, but you still get a good fit to the Stokes parameters. And just look at the contrast, and you have a contrast that ranges from 2.5 to 6.3 kilogauss. I wouldn't dare to say that there's anything like a unique model. And the worst of all, if you look at 53 CAM and the ion abundances derived from exactly the same set of observations, but of course all spurious because of the field that's neither force-free nor divergence, 0. And this from the same group, Kochukov and Piskunov, both in Uppsala. There's nothing in common. But they got satisfactory fits to the profiles. Yeah. And then almost at the end, can semi-Doppler mapping ever recover complex structures if you assume, for example, this really complex abundance structure, and if you invert it with one line and just Stokes I, then you just recover one of these. If you use 2 lines and also 4 Stokes parameters, and if the magnetic field is perfectly known, and so instead of 160 points, you have now 1280 points, that you can use that contain information, then you still cannot recover it. So, and the RMS scatter of the fit to all four Stokes parameters is better than 10 to the minus 3. So, yeah. Let's put together what have we found. Stokes IQ UV spectra provide a lot of information, but the ZTM inversions are still highly underdetermined. And then the abundance stratifications depend on the local field directions and strengths, but also on field-dependent mass loss. And so we have a multiplication of the number of unknowns. For example, if you have typically 1,000 pixels, you have for each pixel 50 abundance points you have to determine. So that's quite a lot. And Tikhonov regularization in any form proposed so far is inadequate and, in addition, at variance with physics. And so, then it has also to be said, ZTM algorithms have displayed an absolute lack of considerations for horizontal equilibria, as I showed you with how to avoid iron hurricanes. Well, iron hurricanes don't exist, so the star has to find a way to establish this equilibria without these strange abundances. And finally, what would have to be done? All inversions have to be redone with the correct formula. It is with adopting potential fields, because for force-free fields, you cannot assume a priori some force-free field. It evolves with time, and you have, yeah, you cannot follow the evolution of these fields during the lifetime of a CP star. So you have to adopt potential fields. Then you have to replace Tikhonov with a regularization function that really reflects the physics of CP star atmospheres and is suitable for field-dependent stratifications. There's none yet in sight, but perhaps someone will be inspired. And then you have to carry out tests with realistic, complex magnetic geometries, at least, even if you don't believe in it, but you could use the published complex magnetic geometries and combine it with predicted theoretical stratification. And then you can perhaps meaningfully interpret the recovered ZTM maps, which are all based on vertically constant abundances. But there's one, I call it, hardly can be called test, by Kochukov and Ryabchikova in 2018, who used my stratifications, but doing everything with a center dipole. With a center dipole, not with their geometries, but with a center dipole. It's an outright charade. And yeah. Okay, thank you. Thanks again for the invitation. Gracias. And perhaps you have seen Ada Lovelace, to whom I owe the possibility to make all my calculations. Thank you.
For questions.
Let's see. And are there any questions or?
Yes, William. I'm looking just one question. When you present the results, that I think it's good if we can. I mean, there were a lot of range of magnetic fields, and you showed that there were like the results were varying. I mean, the same data analyzed several times, and the magnetic fields were very different. I don't remember which slide it is. I think it's 40. Yeah, that's
just a moment. If this I come, this one?
No, I think it's, let me see.
That's 53 come.
No, it's the alpha square CDM.
For alpha, you mean
That one.
column when at the quorum? Is it this one you mean?
Yes, that one. The question is if these range of fields that vary a lot is have been performed by the same group, or each date is different because of something.
No, it's all the same group. There's only one code in use. It's a family of codes inverse from 10 to I don't know how far it has gone. And everything is controlled by Ole Kochukov, who has written this code at the beginning. And it was together with Nikolai Piskunov. And then later on, Kochukov took over. And every publication is under his supervision. It's not a free code.
Each date represents a paper?
Yeah, and there are at least, as you can see, there are at least 7 papers with different maps. And with different, as you can see, in one case, 2003 from 1.4 to 7.7, and then 2007 from 0.6 to 3.1, and so on. So every year there was something different. And the same is true for 49 Cam and for a few other stars. All the stars that have been observed several times, there are several different maps. Only, strangely, 53 Cam has never been observed again. And, well, I doubt that everything, it would be an interesting star, but it's hard to explain why it has not been looked again nobody has looked again at 53 Cam. I asked Kochukov several times, why not? He said, it's not interesting.
Okay, thank you. Questions?
Okay, well, thanks again to Professor Martin Stift.
Well, thank you.